So yesterday I talked about the state space representation of. I did modeling of using state space representation on DC motors, precisely separately speaking DC motors. And today we'll discuss about a state space model representation. So in fact, this is some sort of pictorial representation of a state space variables, equations, and output equation. So it comprises of connections of scalars, adders, and integrators. So scalars means the gain blocks. So this type of representation of state space variables allows to pictorially understand. In fact, this is more. It gives a more easy picture that is able to be understood compared to the mathematical equation. So this is some sort of pictorial representation of the mathematical relation of the state space representation. So as seen from the given figure, we see that the state space representations, that the state equation, the state equation and the output equation can be pictorially represented by the following block diagram. So the first step is while drawing the block diagram is to draw the state variable x and corresponding state change. So this can be accomplished by drawing the integrator in between x and x dot in this fashion. So when x dot is given to the integrator block, it gets integrated, and thus the signal at the output will you will get will be x instead of x dot. So after integrating the signal x, if you look at this particular equation, you have x dot equal to a times x, and then you have plus with b times u. So u is the input signal, and of course this is understood that you will be situated at the leftmost side of the block diagram, and will be multiplied by a scalar b or gain b, and then has to be added with the signal ax. So you're going to add a scalar a with x, and then going to add this with the signal bu. So for this, what we do is we pick the signal x. So we have picked the signal here, and then we are going to feed it to the block a scalar a. Now the signal at the output of block a will be a times x, which is fed to the summer or the adder, where this signal coming from the input u being multiplied by b is being added. So x dot, now what you get is ax coming from this side plus bu from this side. Likewise, we have the output equation given as y equal to cx plus du. So we are going to pick two signals from x and u input, and then we are going to multiply these signals, or we are going to place scalars at the path of the signals coming to the output. So for example, you have the signal x, and since we have a scalar c, so we are going to place this c here. So this gets multiplied with x, and then further fed to the adder. This adder has another signal coming from the input u multiplied by t. So this is how we get the output y, and this completes the block diagram representation. So this is a sort of representation called as state space model, a physical representation of the mathematical equations that we obtain using a state space analysis. So now we try to do some more examples and try to represent a state space model in the subsequent slides. So now suppose that you're given this example where you have state change, two variables x1 and x2 are the state variables, and their state change is given by the following matrices A, B, C, and D is 0, and the output equation y is given by the matrix C multiplied by the state variable x. So it is required to represent this particular form into state space model, the physical representation in the form of blocks. So again, using the same concept, the same method that we used in the previous slide, since we know that x1 and x1 dot has a relation with an intermediate integrator. So what you are going to do is you are going to place an integrator, and you're going to feed and put x1 dot to it, the output from this integrator will be x1. Similarly, you are going to have another integrator corresponding to x2, and the input to this integrator will be x2 dot. The output will be x2. So this is known from the number of state variables in the system, and then now we are going to connect them in such a manner that we obtain the state change like x1 dot, which is equal to minus 1 times of x1 plus 1 times of u. So we are going to place input u at the leftmost side, and since we know that x1 dot should be equal to minus 1 times of x1, so we're going to pick a signal from x1 and going to feed this to a block with a scalar minus 1, and this block, the output from this block is further fed to an adder like this. Then we have another signal coming from input u which has a scalar 1. So we're going to place a scalar or a gain block with magnitude 1, and the output is going to be fed to the adder. So this gives us the signal x1 dot. Likewise, we are going to have signal for x2 dot as equal to minus 2 times of x2 plus u. So in this case, you are going to have a block from x2 multiplied by a scalar minus 2, then being fed to the comparator with a plus sign, and then you have a signal picked from u again with a block of gain 1 fed to the same comparator with plus sign. So you have the variables x1 and x2, which are nothing but the state variables at the output of the yet obtained block representation of the state model. And now from the output equation, we see that y, the output is equal to 2 times of x1 minus y minus x2. So in this case, what we are going to do is we are going to add a block at the output x1. So this is the block representation of the given equation. So what we did after obtaining x1 and x2 is that we added a block with gain 2, and this gave us the output as 2 times x1, which is fed to the comparator, and again from x2 you have a block minus 1 at the output side, and thus the signal will be minus x2 fed to the comparator. The signal y will be 2x1 minus x2, which is what we get from this relation. So this is 2x1 minus x2. So this is the required state model of the given state space equations. And similarly, if suppose that you have, let's say, 3 state variables. So in this type of problem, one thing that we can conclude now is that we are going to have 3 integrators corresponding to each of these variables. So your first task will be to draw all the integrators which will be present in the system, and after drawing integrators, the input of the integrators will be given as x1 dot, x2 dot and x3 dot respectively, and the output will be x1, x2, x3. Then we are going to use the same method we done in the previous slides. So x1 dot in this particular equation is given as minus 2 times of x1 plus u. So we are going to pick a signal from x1, multiply it by a gain minus 2, and then give it to the adder. The output of the adder will be x1 dot, and the other signal will be picked from the input u multiplied by the scalar 1 given to the adder, the same adder, and thus you finally get x1 dot in this manner. And similarly, you are going to obtain x2 dot and x3 dot, and then if you observe, after obtaining x1, x2, x3, which are nothing but the state variables at the rightmost side of the block diagram, using the output equation, you will be forming the block representation, the final block representation of the state space model. And since y is equal to half of x1 minus 1 of x2 plus half of x3, and thus the respective blocks will be placed at the output of the respective state variables in order to obtain the output y. So this is done in this manner. So you're going to have this block corresponding to the state variable x1, this will be corresponding to variable x2, and this will be correspond to variable x3, and then you have the output y and input u. So I guess this part is clear to all, and if you have any doubt, query related to this portion, you can ask me now. And if not, I move forward talking about conversion of transfer function to state space. So till now I told you that you have different sort of representation of system, one of which was transfer function, which was studied in unit 1, and the best form of representation till now we saw was state space. So if suppose that you're given transfer function of any system, then you can acquire state space representation of the system using transfer function. But still that would be having drawback which we studied is associated with transfer function. One is that in case of transfer function, since we know that in of representing only one input and one output, and all the initial conditions are always taken as 0, and thus the same thing is going to be happening when we are going to convert the transfer function to state space representation. Since transfer function is obtained by having certain assumptions, so those assumptions were 0 initial conditions, system must be having single input, single output, and others. The system should be a linear time invariant system. And thus this means that once you obtain a transfer function for any system, you already have assumed that system to be a linear time invariant system having 0 initial conditions. Thus, if you convert that transfer function to state space representation, means that you are assuming the system to have all the conditions valid for transfer function to be included in the state space form. So suppose now we are given an example. The state space representation is desired to be found for the given transfer function C by R, which is given as 24. There are two cases for conversion of transfer function to state space, one of which is if you have in numerator a constant, like the given example. So the second case is if you're going to have a polynomial in the numerator. So in this example, since we have a constant in the numerator, so such type of problem are straightforward as discussed below. The solution is given, and for if suppose you have polynomial in numerator, that is case 2 and will be discussed after this problem. So if you cross multiply, so the problems of such type are done by cross multiplying the numerator and denominator. So CS being multiplied with the denominator on left hand side, right hand side, and RS being multiplied with the numerator on the right hand side, and thus you obtain this relation. If you take inverse Laplace transform, so you are going to assume initial conditions to be 0. So this should be 0. I forgot to mention 0 here. Assuming initial conditions 0. So if you're going to take Laplace inverse, then what you get is corresponding to S cube, you will be having the third order differential. So this is nothing but d cube by dt cube of C plus 9 d square by dt square of C plus 26 d by dt of C plus 24 C equal to 24 R. And now C and R, which is written in a smaller case, are in time domain, while capital C and R were in Laplace domain. And since after obtaining the differential equations, we learned that we can assign certain state variables to such type of problems, because we desire to convert nth order differential equation into n first order differential equations, because this is the only way we are going to find the state space representation. We are bound to represent the higher order differential equation into first order differential equations. And thus, in order to do so, we assume certain state variables like x1, x2, and x3. So x1 can be written as c, x2 as c dot, and from this we get x2 equal to x1 dot, and x3 is equal to c double dot, and thus x3 will be equal to x2 dot, while x3 dot is nothing but c triple dot, which can be obtained from this equation like this. So x1 dot is x2, x2 dot is x3, x3 dot is from this equation minus 24c minus 26c dot minus 9c double dot plus 24r, which is written here. and in place of C dot we have written x2, in place of C we have written x1, in place of C double dot we have written x3. So using these equations for corresponding to x1 dot, x2 dot and x3 dot, we can populate the matrices corresponding A and B as shown. So x1 dot is equal to x2, and thus we get 0 1 0 since 1 is being multiplied with x2 and 0 with input. Then you have x2 dot equal to x3, this gets 0 0 1 and this is 0. x3 dot is equal to minus 24 x1 minus 26 x2 minus 9 x3. So you're going to place each of the coefficients associated with the state variables like minus 24 here, minus 26 here, minus 9 here, and then you have a coefficient associated with the constant r as 24, and then you have the final output y equal to c, which is x1. So this is written as 1 0 0 because you don't have any components of x2 and x3. So I guess this clears the problem. And now since we were required to uh, show these into some state models in the form of block diagrams, so we are going to use these relations to obtain the block representation or the state model representation of the system. So again, in the similar way, now since you are talking about three variables having three state changes, and thus you are going to incorporate three integrators in the system. But now compared to the previous examples that we did, we had a relation of state changes with their own state variables. For example, we talked about state variable x1 dot, which had relation with x1 itself. But now in this case, we have a relation x1 dot, which is equal to x2. x2 dot is equal to x3, which means that after placing integrators, so let me do this for you. Suppose I assume integrators corresponding to, let's say we fed signal x1 dot to it. So the output of this integrator will be x1. If you have the second integrator with input x2 dot, the output of this integrator would be x2. And likewise for x3, the input is x3 dot and the output is x3. So this is integrator. This is x2 and this is integrator. Now if you look at this relation, you have x1 dot which is equal to x2, which means that this signal is nothing but it's equal to x1 dot, x2 is equal to x1 dot. Likewise, you have x2 dot equal to x3, which means x3 will be equal to x2 dot. So from this it is clear that these three integrators will be connected in series in such a manner that x2 will be connected at point x1, x3 will be connected to the point x2 dot in this manner. So you have x3 dot fed to the integrator, and the output of this integrator x3 is fed to another integrator, which is nothing but x2 dot. This is equal to x2 dot. Then again fed to the integrator gives you x2, and this x2 is nothing but equal to x1 dot. And then again an integrator gives you the variable x1. So after obtaining the three integrators connected in series, you are going to place the constant coefficient blocks using the equation x3 dot. Since x3 dot is equal to minus 24 x1. So since this is x3 dot, you're going to pick a signal from x1 and connect again minus 24 to it. So you have x1 here, you connect again to it, then you're going to feed the signal to the comparator with a minus sign because you have a minus sign here. Then again you have a block connected to x2. So you have this signal x2 fed to the block minus 26, again given to comparator with a minus sign. Then from x3 you have a block 9, since you have a coefficient 9 here and with a minus sign, thus this is why you are having a minus sign in the comparator. And the signal is plus 24R. So you're going to place the input R at the leftmost side, and this input is then further fed to the block 24, which will be fed to the same comparator with a plus sign, and this will give you x3 dot. And now you, after obtaining the state equations represented into state model, the last thing is to obtain the output which have relation with the state variables x1, x2 and x3. Since we see that y is simply equal to x1 only, and thus x1 will be given as output y. So this will be completing the block representation of the given transfer function in state space form. And the second is, if you suppose you have a polynomial in the numerator, then how are you going to represent such type of transfer functions to state model? And I guess this will be discussed in the next class. If any one of you have question, you can ask me.